Mine will be on computer, yours will be on cloud. Yep.
Okay.
So,
Yeah.
okay.
Yeah. Hang on a. Okay. All right. Right. So I think before we let me just press this. Okay. Oops. So before we start, I would like to welcome all of you in this joining us in this event on a beautiful Monday afternoon, I guess. So I hope everyone is staying healthy and also keeping yourself safe from the COVID situation in Singapore. But of course, as it becomes an endemic in the future, I think we eventually hope that we can meet each other outside, right, and really discuss further into what material science is all about. All right, so my name is Vincent. I'm a faculty staff at NUS, Material Science and Engineering. So it's my pleasure that I'll be giving you the opening speech for this event. Right, I'll be giving you some information about what material science is all about. Okay. So this is our very first material science, or rather material innovation and engineering challenge, 2021. So this is the first event that we are doing, and of course, we would like to receive your feedback after you have completed this challenge. Okay. So without further ado, I think I will just give you some ideas of what we are planning to do for these 3-hour sessions. So our very first thing that we'll do is basically a welcome video by the dean, right? So we'll watch a video about him, and then I will walk through what MSc curriculum is all about. Then after that, we'll invite our lecturer for this event, Yong Hao, to discuss about what is 3D printing and how do you use computer assisted design, and also to use the finite element analysis in this challenge, right? And lastly, we will ask you to meet up with your student ambassador. So basically, please try to name yourself according to what you have submitted to us, and also tell us where you are from so that it's easier for us to assign you to the breakout rooms, all right? Okay. So first, let's look at or watch this very short clip, about 3 minutes clip, about the introduction to material, or rather, the introduction to engineering by our dean. Let me know if you can't
Engineering
hear
is
any
about
sound.
solving some of the world's toughest problems. But the challenges engineers face are becoming more complex. So at NUS Engineering, we are transforming how we train the engineers of the future. Hi, I'm Aaron. I'm the Dean of NUS Engineering. As engineering challenges evolve, engineers need to draw on an ever broader range of skills and knowledge. So we have reimagined our curriculum. For students starting in August 2021, you will have a bigger range of options than ever before. We think of it as your opportunity to build your own degree. You'll have the flexibility to study both the traditional engineering disciplines while broadening your skills in other areas. NUS Engineering is already ranked in the top 10 globally for engineering. It's #1 in Singapore for graduate employability. We have a world-class faculty who are global leaders in cutting-edge research, such as biomedical engineering, medical technology, quantum engineering, and advanced materials. Over the past year, many of our faculty have stepped up to join the fight against COVID-19, developing new testing kits, therapeutics, and protection equipment designed to keep frontline healthcare workers safe. As an NUS engineering student, you will engage with and learn from these experts. We have access to the latest digital technologies and labs. From day one, you'll be exposed to hands-on engineering using robotics and drones, and work on other cool projects that will build your foundational knowledge. NUS Engineering is at the heart of a global network with exchange programs with leading engineering schools around the world, strong ties with NUS Overseas College Program, and industry connections that offer access to a world of exciting internships. At NUS Engineering, we're here to help you discover your passions, to build your skills to the best you can be, and go where you want to go. So please come join us. We're looking forward to building the future of engineering with you.
So this is a very short clip about. So this is a very short clip about engineering in general. That's shared by our Dean of Engineering, right? So I guess we'll move on. So basically, material science and engineering in NUS is one of the so-called the top university in Asia. So of course, we want our students to learn, and we usually have our world-renowned experts, okay, from all over the world, and you get a chance to learn from them. Okay, and I think another thing that I want to highlight is the research opportunity. So here in NUS, we have a lot of wide variety of opportunities for you to conduct research and also to explore your interests in different areas. Okay. And I'll just zoom into what material science and engineering is all about. So I think most of you should briefly understand what's material science, or you have already done some courses in material science in your polytechnics. So I'll just cut to the chase, a simple one. So here in just the material science itself is to understand the material that can be found in the nature based on its physics and chemistry, right? So how do we utilize these materials and make it into something that is functional? So right now, I think most of you should have heard of Tesla trying to make a more sustainable battery that can last longer mileage, right? So these kind of materials are very important in material science, right? So how can material science help in achieving a longer lasting battery, for instance? And I think with the COVID situation arising back again, right, in Singapore, I think here we are interested in coming out with smart sensors like biosensors that can be attached to skin, so can detect any toxins or virus in the air, right? That can be used. That we'll use material science to explore, right? I think another area that we are quite interested in is how to build a rather sustainable food technology for space exploration. So I think most of you should have known that there's a plan to bring human to Mars. So the question here is, how do we sustain the humans in this exploration with food, right? So one way that we can do it is to come up with a kind of material that can be used as a soil, right? And this soil can then be used to give you the crops to sustain this space exploration. So I think here what material science is all about is basically trying to find out how the science behind the materials and utilize this knowledge and make something that is functional for our future development. Okay, I think this is just a more information about what material science is all about. So if you have a material science, it's basically another way of saying that you have kind of knowledge in all the different areas that is shown in this colored the circles, right? So material science here, basically you are trying to fuse all this knowledge into one, right? So just in brief, right, what this means is that in material science, we are interested in the processing of the materials, but of course, when we process the materials, the next step that we should consider is what is the structure of that material that we produce, right? And then we use characterization techniques to study for their properties and then relate these properties to a given performance. So that's what material science is actually, in short, is trying to achieve. So here, I think for the next few years, right, what we are aiming for is to achieve a flexible modules. So what we are saying in general is that out of the entire curriculum, you have 25% of this curriculum meant for something that is unrestrictive. So what this means is that you are able to use this like the 10 modules in general, right? 10 modules for you to explore your own interests. It could be, the AI, computer science, or it could be business, right, or economics. So these are some things, some highlights that we want to really showcase to all of you. And of course, for our material science, that will be 37.5%. Okay, and then you have the rest of the 37.5% that is given to the common curriculum. So in our common curriculum, you are able to have a chance to learn about artificial intelligence. That's what our Faculty of Engineering is aiming for. So for most of our poly students, if you were to join Faculty of Engineering in general, not only pertaining to material science. So if you join Faculty of Engineering, if you are accredited, then of course you will be given 38 advanced placement credit. What this means is that you shave off 1 year of your studies here with us. So our poly students usually only take 3 years honors with us, and yeah, and you will graduate, right, by then. So this is just a very quick summary or general overview of what how our Polytechnic students will most likely to go through if you take a course in Faculty of Engineering, right? So I think I want to really highlight those that are in gray. So these grays are those modules that give you the flexibility to learn things that you are interested in. And then I also highlight those in blues. The blue ones are those that really the common curriculum that our faculty has identified as a very important or essentials topics for the future, right? I think here you can appreciate like system thinking and artificial intelligence, right? And I think the way that Singapore, or rather the world, is aiming for is towards a sustainable futures. And that is where we are also introducing this module in our curriculum. Right. So out of this, of course, we have our own material science modules, those that are in the purple. Well, I guess for mostly for our poly students, they are actually very, very interested in the individual research. That's what I understand. So correct me if I'm wrong. So I think individual research project, meaning the final year project, will be one of the highlight for our students, right? So currently, our material science, okay, more specifically for material science, we are looking at 3 different specializations. So what this means is that our students, if they were to join us, they have the opportunity to choose one of these 3 specializations. So for instance, I think there's a big hoo-ha about the artificial intelligence. Of course, go for it, right? If you're interested in it. But let me just point to you the importance of the other 2 specializations. I guess polymeric and biomedical materials is something that is quite, well accepted, that it's very important at the current situation, right? So like how the material, what's the material used to fabricate a good mask, right? Could be something of interest. So that is something that if you're interested in, you can always go for it. But let me just focus more on the nanostructured materials. I think nowadays materials that we have, they are in some kind of a bulk materials. So if you have a bulk materials versus a nanostructured materials, you see that the properties will be very different, very, very different. So that is where, if you take up this specialization, you are able to get yourself, more familiarized with the nanostructured materials. You get the chance to fabricate nanoparticles, and you also get a chance to use cool machines like the transmission electron microscopes. Okay, and look at it, right? That would be cool, right? So end of the day is that if you were to take this, you just need 4 modules. basically to complete the specializations, or rather 5 modules. I'm so sorry. So in material science, I think as the name suggests, right, our course is called material science and engineering. So we encompass both the science part and the engineering part. So science is more of the asking why, right? So why these materials have such a property, right? So to understand the science behind what we observe. And then we have the engineering, and that is to understand, or rather to ask the question of how to put them together. So this is just a very, just a cartoon to show you how you'll fare if you know how and why. Okay, so if you know how, you get a job, right? You know how to do it, that's great. So if you know how to do, or if you know the reason behind that, you also get a job. But if you know how to do it and why you do it, then you will be the leader of both of them, right? So that's actually what the cartoon is trying to say. So at least in our QS ranking, okay, NUS material science is one of the, actually it's a top in Asia, right, for employers' reputation. So our graduates are actually highly sought after. And this slide is just to show you that we have a very well-equipped lab in material science, and we really focus a lot on education, right? I think the career prospects are something that we are all interested in. I'm not sure which you are in. If you are in the year 3, probably you are looking at which course to go through in the future, which university, right, to go to. So at least for our statistics, right, is that our median salary is about 3.9K, right, and we can achieve 90% employment rate. That is based on last year's statistics. So of course we have our graduates working in different areas. People may ask me why Google. So well, Google, they really like people who are logical, right, and people who are able to string a series of thought together. So of course, you can't really be a computer engineer there, but still you'll be able to go there as a management level. So I like to emphasize some of our graduates are actually in the ST engineering. If you're interested in defense sector, I think that's where material science is really important in this engineering sector. Okay, you have a few engineering defense sectors here, like A-stars as well. And if you like more commercial things, there's Johnson & Johnson and P&G, right? These are all really good companies that our graduates will be able to get into. So as for internship collaborations, there are a few, of course. I think if you're interested in semiconductors, you have all these companies. If you're interested in defense, you have all these companies. And if you're interested in the commercial applications, or rather commercial industries, then this is where you can go for. So I think, yeah, what we are trying to really go for is that if you remember our very first few slides, we talk about you get to learn from our world leading material scientists. So here are some of the news that we have retrieved from our website. I think you can find on the web as well. So I think out of these 5 people, you should know there is one Nobel laureate. Okay, so the Nobel laureate is here. Is Prof. Costia. So if you heard of graphene, then probably you should know who is he, right? So he won the Nobel laureate because of the discovery of graphene, right? So Prof. Costia is in our department. So if you are interested in graphene, or you have always been fascinated about graphene, then I think you get a chance to talk to him, right? And even if you don't join us, it's fine. You can let me know. We will just let you get you his email address, right? Then you can converse with him. So in 2021, if I'm not sure whether you all heard of the Nature. Nature is the one of the top ranking journal in the world. So Nature has indicated that NUS is one of the top 10 universities based on the Nature Index. So this makes us very prestigious, right? And that is where research is really one of the top focus at NUS. I think more recent news is this. I'm not sure whether you heard of this, but we are coming out with a new material science research center at NUS. So this center is basically for the functional intelligent materials. So this is the world's first institution, right, that really helps in the development of these functional materials. So I'll just give you the quote from our NUS president. So this our NUS president has said that material science is going to play a very important role in addressing our global challenges, and material science, or rather material research, will be one of the key areas in the future at NUS, right? So I think with that, let me just conclude that part of introduction to what material science at NUS is all about. All right, I think this is something that y'all will probably be more interested in. That's the event flow for this competition. All right, so we are at phase one. Phase one is the lecture where we will we start from 3 p.m. Then we try to end it by 6 p.m. Then we will, for phase one, I split it up into phase 1A and 1B. So phase 1A is where you have the design stage. So after this, after today, you will probably learn about CAD and what's FEA, right? And based on this knowledge, you are able to go into a design stage. We will attach a student ambassadors to help you in the design. So you will have about 7 days to do this, right? 11 to 17 October. Please take note of the time. So during this period, please do not be shy. Contact our student ambassadors if you need any help. So phase 1B is where you have to submit your design to us, right? So we will release this information to all of you again later on. No worries, right? So on a Sunday, 6 p.m., please submit your design to these 2 emails, right? Please take note of this. This is the deadline, right? Then phase 2 will be the printing stage. So the printing stage, we do not require all of you to do anything, okay? So if you feel that you are interested in understanding how the printing process is done, well, you just let your student ambassador knows. If we can allow it, we will allow you to come down to NUS and take a look at how all this printing is done. All right. So this printing process will take up the 2nd week of the challenge. And then please take note, for phase 2A, we will have an online competition. So what this means is that once we have all this printed out, we'll take a photograph and we'll post it on the Instagram. All right. So basically we will come out with the award, which is the most liked design, right? So the most liked design will get something in this competition. So make sure you get your friends, or you can just upvote the post whichever design that you have done, right? So that will be a 24 hours competition, online competition. So that will occur on a Friday, right? So we will let you know again the dates, okay, in another separate email. Okay, so finally, the phase 3 is where we have the virtual challenge, the virtual live demonstrations. So we release the Zoom link to all of you in a later part of the week. But basically what we are trying to aim for is, of course, to do a physical demonstration to invite all of you to come down. But the problem is, I think it's rather unsafe for us to do this. So this will occur on a Saturday, 9 a.m. So yeah, just please join us, right? Because we have to ask the team at which height do you want to drop your egg from, right? So phase 4 will be the prize awards, the souvenirs, and we will give you another 3D printed copy of your design so that you can view it later on and you can play with it. Okay, so we'll do this, we'll mail it to your school. So that will probably be during the early to mid-November. All right. Okay, so I'm not sure. I think most of you should have known the objective of this competition is to design an egg sleeve that can protect an egg from impact, right? So this impact is a drop, a free fall from height. So the judgment, or rather judging, will be based on the highest survival drop height. So when we open it up, we inspect the egg, there should not be any cracks. So if there's any crack upon inspection, regardless how big or small this crack is, we will take the previous height as your the highest survival height. Okay. Then I think in this event, we really hope that you can use the finite element analysis to help you in the design. Okay. So later on, Yonghao will be talking more about this. So with that, I wish you all the best for this competition. All right, so for this event, let me please introduce our lecturer. So he's Yonghao. So Yonghao is our PhD candidate from NGS. All right, so he was previously our material science undergrad, and I think based on his FYP, he has found it interesting and he wanted to do a further study, right? So currently his research is on 3D printing, or rather more towards the metal printing, right? Okay, so with that, let me welcome Yonghao for his lecture.
Okay, thanks, Vincent. Okay, yeah. Then I'll share my screen. Yeah, so let me just share my screen. And let's go into. So, okay, I hope everyone can see my screen. I mean, for the students, if
I can see it.
I mean, thank you all for coming for today's lecture. But actually, I don't think of it as a lecture. I think of it more as a sharing. So I mean, if you want to, you can on your cameras. If you want to, you can also jump in anytime. You can either use all the the raise hand function, or you can just unmute yourself and just ask whenever you have any questions. Okay. Basically, I hope this won't be too boring. I subscribe to the idea of edutainment, so we can be entertaining but education at the same time. Okay, so today's talk or sharing is just basically about 3D printing. Okay, so how you bring your ideas into reality. So actually, personally, this is not just my research. Okay, maybe more than my research, this is my hobby. I guess that's why I'm here. Because actually, I'm sharing about something that I like. So let's go right into it. So the outline of today's presentation. First of all, I'll just give a brief overview, of what is 3DP. We think we know what is 3DP, but do we really know? And just what do we use it for? And what kind of materials actually are we using it with? This always surprises me. People seem to think that it's just plastics, but you'll be surprised. So for this challenge, we'll be just starting you off basically what is the most accessible 3D printing technique. So that's FDM, and then I'll just tell you about how FDM works in general. Actually, it's very simple, and then some design considerations, how you want to think when you are thinking that you are trying to print something. So what are the concerns? And then finally, for the last part of this lecture, I'll be talking about Fusion 360, which is CAD software. Basically, I'll just be telling you where the buttons are. So learning where the buttons are is half the battle won. And then actually there is a simulation interface right within Fusion. So even if you've never done finite element analysis, even if you're not a certified mechanical engineer, you can use simulation to help you in some manner. Of course, the more you know about it, the more you can do with it. But even for someone who is unfamiliar with FEA, you can be surprised what you are able to do with it. So what is 3DP? So, I mean, I would really love someone to tell me, but I guess people won't be unmuting themselves yet. So another question, what is it used for? And the question, is it new? And what is its significance? So 3D is actually a very broad term that covers many material shaping techniques. The key term is shaping. Okay, we are making shapes. And when I highlight many, it's because there are many techniques. And every year or every month, you seem to be hearing about a new technique. Most of the time, it's very similar to some old ones. But people are always coming up with new ways to do 3D printing. And what is it used for? So the original name for 3D printing, other than just this popular term of 3D printing, it's actually rapid prototyping. So it used to be used for making prototypes. So what would my design look like, but it wasn't meant for actual use because they couldn't really make it in the material that they wanted. But nowadays, 3D printing has a new name that is more commonly used in the industry now. So it's actually called additive manufacturing. And is it new? The question, well, actually the first 3D printing technique was invented in 1978, if I'm not wrong, by Chuck Howe. So it's actually SLA. Some of you might know it. Basically, it's another plastic printing technique. Yeah, so 1978. And I think within a few years, there was also metal printing. So metal printing existed since 1980s, but only in the late 2000s, we begin to see some more action from 3D printing. So, but I mean, is 3D printing really that significant? Or is it just used for printing toys? This is something we have to think about. Before we go into anything, we need to always think about actually what's the use. But I'm glad I'm able to tell you actually that 3D printing is pretty significant. Maybe it's up for debate just how significant it is at the current moment, but I think it's undoubtedly something that will help humans advance technology in the next few decades. So we all know that actually mankind rely on technologies to help shape and manipulate on our environment. So actually the chair you're sitting on, maybe it's a secret lab, maybe it's not. They're opening out an R&D lab in Singapore as well. So even chairs require R&D, but even then, chair materials also have their own tricks, tips and tricks that you need to know in order to make a good chair. Of course, whether the chair costs $700 is another issue, but it's important, what we can do to our surroundings that determine our technological level. So there are material ages that some historians use to classify history. So first of all, there's a Stone Age. So we take stones, rock, prehistory. They use it to make tools. Okay, flint, like flint stones. Okay. But after Stone Age, what is the next age? The next age is actually the Bronze Age. Bronze is an alloy of copper, but it's not pure copper because pure copper is too soft. Okay, you learn more about alloying if you do join us. Okay, so they take actually metals also come from rocks, because they aren't just found as metals in nature. Okay, but they are found as ores, some kind of compounds from which we extract the metal. So of course from copper ore, we can make even better tools, But of course, in the Bronze Age, you can see that all these examples are basically weapons. People make better weapons to kill each other with. Whoever has the sharpest tool basically is the biggest guy in the park. But then, we move on from the Bronze Age to the Iron Age. So actually, the stone, bronze, and iron ages are used to classify the prehistory or up to around 600 BC. But actually, the Iron Age stretches all the way until now, because we are right now in what we call the Industrial Age. So all the machines, factories. That's because we use a lot of iron. We use a lot of steel. Do you know that steel is the most widely used engineering alloy? Well, it is used in by the metric tons. Okay, but so with iron and steel, we can make a lot more things. And the Industrial Revolution, steam engines, all these things are made of steels or iron. But are we still in the industrial age? Well, some people say that we are now in the information age, but how do we get our information? So actually, I would like to call this the silicon age, and where do we get silicon from? Silicon, we can find it in sand. It's very cheap. Sand is basically quartz. It's silicon dioxide. Well, but where, how do we enable sand to, give us all this amazing technology that we have, in this computer that I'm using to present from? Now, because we can make it into transistors, we can make it into wafers that we can etch and make nanometer size transistors. And all this, you can see, is dependent on our technology to not just process materials, but also to shape it to whatever shape we want, because transistors have their own shape, right? But do you ever wonder why, when you walk out, things look the way they do? I just talked about shapes, right? But do you ever wonder why these shapes are, why is it this shape? I mean, we walk past railings all the time, and of course, some of these railings are disinfected often, so you can hold it. But if you hold it, you realize that when railings have this kind of a joint, what do you notice about it? You'll notice that actually it isn't one piece. Railings are often welded together. Then you'll be surprised. Even for a simple shape like railing, we have to make it in multiple pieces. But why do we make it in multiple pieces? Well, it's because actually there is trouble making it in one single piece. And that's actually because we have a lot of trouble making shapes that we actually want to make. Just due to the fact that material processing techniques, shaping techniques are quite limited. They have their limitations. Of course, we can do a lot of things, but they are still limited. So, for example, the designer, after you spend some time thinking about what you want to do, it will come up with a wonderful design. Wow, it's so complicated. It's designed for function. This is exactly what you want. And then, you pass it to the engineer, and the engineer says, yeah, great, I can do it. And, after a few months, because traditional manufacturing takes some time, maybe after a few months, then you finally get your product. And you get a product that maybe doesn't look like what you originally planned for it to be. Of course, this is a dramatization. The real engineering process doesn't work like this. But some of you might have heard of the term design for manufacturing. There's a long definition for it, definitely. Some of you might even know it. But actually, it's just all about telling you what not to do. That's because for different manufacturing techniques, they have their limitations. They have their geometries that they can make, they cannot make. So design for manufacturing is actually all about trying to design the part for the manufacturing technique and not for the application that they're going to be used for. And that is where actually 3D printing brings a lot of value. It's because 3D printing allows us to break away from design for manufacturing, and it gives us much, much more freedom to think about what shape we actually want to make for the application. So the 3D printing, so the here and now, some of you, I think most of you are probably quite young, okay, but 3D printing, basically the hype started when I was in undergrad. So maybe it was in 2015, maybe, yeah, it was in 2015 when it became very hot. So there were actually two waves of hype. So the first wave of hype was people started to make very cheap plastic 3D printers, and hobbyists could buy them. That was in early 2010s. Then people started thinking, well, the future is now. You can make things whatever you want in the comfort of your home, and you can, but actually, the second wave of 3D printing, and what I would consider the more significant one, is actually when, I think, yeah, 2015, around there, when metal 3D printing became more mature and the quality improved significantly, the speed, people started to be able to print faster, because actually 3D printing, the process itself can be a bit slow, but it's been increasing significantly, and mainly the materials. So like I said, metal 3D printing. So metals are important engineering materials, so we find everywhere. But for a long time, 3D printing, like I said, 3D printing metals existed since the 1980s, but accessible 3D printing and quality 3D printing only began in this decade. And that really opened up, many doors for 3D printing. So for aerospace, I think it's not over exaggeration if I tell you that every aerospace company or every company involved in making planes or making parts of planes, they are involved in 3D printing, and 3D printed parts have already made it to the skies. Some of you might know that aerospace industry is very highly regulated because they're dealing with a lot of lives. The plane, it fails, hundreds of people might die. So all the parts and all the manufacturing procedures need to be very heavily regulated and quality assured. But 3D printed parts have already made it to the skies. So this engine nozzle you see here is from GE, General Electric. So this is their LEAP engine. They've already made many of these, and these are all flying already. So it's made of titanium. So it's made of metal 3D printing. But it's not just metals that are taking to the skies, you see. Plastics, so aircraft interiors. So this is some examples by the company 3D Systems. You can see all these air ducts, wall panels, armrest caps, all these things that you think you might not even notice in the airplane, but they're all very important for your comfort and all important for the the operation of the airplane, such as the seat framework. And 3D printing by plastics, engineering plastics have allowed the aircraft to become lighter, and lighter aircraft requires less fuel, and less fuel means more sustainable business and of course a lower cost. That's why actually aerospace is the biggest driver of 3D printing. You really see a lot of value in it. The second one, of course, is biomedical. And why biomedical? It's because one beautiful thing about 3D printing is that you can make individual parts for individualized parts, for everyone and anyone, basically at no extra cost. Conventional manufacturing relies on making the same part tens of thousands of times, and that's where the cost savings come from. You make a mold, you make a single part, it's going to cost a lot. Like if I made 100 parts, the cost will drop. But if I made 1,000 parts, it's cheap. But that's where the problem comes in. Conventional manufacturing is all about making tons and tons of parts, but all these parts are they're not made to order. It's just this same design. I'm making this design and that's it. And you think about the human body. I'm not sure about you, but when I go to buy my shirts, buy my pants, I always can't find my size, or it's not bespoke, it's not well fitting. And if you think about the discomfort about pants, think about someone who has lost a limb, lost an arm, lost a leg. They need a specially tailored prosthesis, for them to go about their daily lives. But traditional prostheses were ill-fitting. They were very non-functional, and some of it was quite heavy. So actually, I think many people don't really like to use it. But 3D printing has really enabled, the making of really advanced, lightweight, functional prostheses that's really changing the lives of many out there. And dental industry, there is a NUS spin-off, Structo. They make basically 3D printers for dental applications. I think the last I heard, they had some funding, 40 million. But dental industry, everyone we have our own, teeth, shape, everything, size. That's why 3D printing really comes into its own. It helps dentists make new aligners, molds so fast and so convenient. It is really transforming the dental industry. Automotive, maybe not to the extent as aerospace, but I don't think it's a lie if I told you that every automotive company is dabbling or using 3D printing already. Either they're experimenting or they're already using it. So for example, this engine inlet is by Ford. It's an entire engine part made up of aluminum, also by metal 3D printing. And then there's a seat bracket by Audi. So you can see on the left-hand side of this seat bracket image, it's a conventional seat bracket. Do you see what I just said about shapes? It's very simple. It's a flat rectangular piece that's bent. You can see how much material it's using. And most of the material is in fact redundant. It's not there because it serves a function. It's there because we can only make it in this way. But on the right-hand side is the 3D printed version. We can design it so that we only use materials where we need it. And this results in a lot of cost savings and also performance improvements. And also for marine, Singapore is a port country. We rely heavily on our port. We're also very interested in this. On the this boat frame was 3D printed in the US. It's the entire boat frame was 3D printed in engineering plastic. It's actually seaworthy. I think it was printed in a matter of hours, so it's very fast. And on the right-hand side, it's a ship propeller. So it's made by wire arc additive manufacturing, or WAM. So it's actually a type of additive manufacturing technique that it's used for repair. So sometimes ship propellers are damaged. In the old days, maybe they just scrap the propeller. But nowadays with 3D printing, we can actually repair the part at lower cost and shorter time. So that's here and now. But where can we start? Nowadays FDM printers are so cheap. I even have one at home. Okay, but if for those of you who have not had the experience with 3D printing, FDM is really a good place to start because it has a lot of things, has a lot of concepts built in that applies to other 3D printing techniques, and it's very accessible. So FDM is also called fused deposition modeling. It's actually a trade name by Stratasys, the company who originally invented this. But of course, there are a lot of companies in China who are also making very cheap machines. That also, I happen to own one. But I mean, other companies also come up with FDM printers, but sometimes they don't call it FDM because FDM is trademarked. Sometimes they call it FFF, or fused filament forming. Basically, it's the same thing. Name's different, but the idea is the same. So what exactly is FDM? So this is the machine that we're using for this 3D printing challenge, okay? So this is a Prusa i3 Mark III S, okay? And if you think about it, actually a 3D printer or FDM printer is actually very simple. Do you know if you go online, you can actually find the resources to build one yourself, not buy one, to build one from scratch, okay? This is because first of all, what you need is the x-axis motion. So in this case, the build platform is going to slide forward and back, and that's the x-axis. And then your printhead is going to travel along the rails, and basically that's the y-axis motion. And for the last D in 3D, the printhead can go up and down, and that's a z-axis motion. But where does the business end of the printer come? So this is the business end, this is the hot end. So this is a direct drive 3D printer. This means that the extruder motor is mounted right on top of the print head. So the extruder motor is just a gear assembly, of course, driven by a motor that pushes filament into the print head. So the filament goes in from the top, exits at the bottom of the printhead, which is heated to the melting temperature of the filament. depends on what plastic you use. You'll set the printhead to that particular temperature. So for common plastics like PLA or polylactic acid, it will melt at around 185 to 215 degrees Celsius. So on one hand, we have 3D positioning of the printhead within the build volume, and we have solid thermoplastic filament, that is being melted and extruded. And then we can get our 3D printed part. So the materials for this challenge, it's plastics that melt. Okay, so we call this kind of plastics thermoplastics. Okay, there are other kind of polymers. Okay, so there are thermosets, UV curable type of polymers as well. So some of you might have already dabbled into 3D printing, and you might know things like SLA or MSLA or DLP printers. So those printers that you can also get for yourself, also at very low cost, less than $500. Those use a light source to cure the plastic. So you pour in resin, and then it's cured to become a solid by a UV light source. But of course, resin is quite messy and toxic to work with. Thermoplastics, on the other hand, you have filament. The filament is solid, and you load it on. It's nice, I guess. It's fuss-free. And among all these fuss-free polymers, there are 3 kinds that we'll be allowing you to use. So you have to pick from these 3. So when you mail us your design, you have to tell us specifically what plastic you intend to print with. And all these plastics have their own different, characteristics, different properties. So we have PLA, polylactic acid. We have ABS. I forgot the name for it, but it's short form of ABS. There's also PETG. So PETG is, you might be familiar with PET. Most of your Dasani bottles, your mineral water bottles, they're made from PET. So PETG is just a type of PET. So when you think about what plastics to use, it's dependent on our design. The design requirements, how strong should it be? What is my part supposed to do? It will affect the material choice. And what material you have available to you will affect how you can design the part. Some of you might already know, there are flexible filaments. So there are plastics that we can print that are very rubber-like. But on purpose, we are not allowing you guys to use these rubber type flexible filaments for a very simple reason, just because those materials are very well suited for this particular challenge. And if we allowed you to use it, basically everyone will use it. Then there's no fun, right? But it's not to say that rigid polymers can't do the job. Of course, if I allowed you to print with a rubbery polymer, definitely you will be able to survive much greater heights. But what can we do to maximize what we have? We don't always have materials that we want, and that is true even in industry. But how do we work with what we want? So what kind of material properties do we look at? So I mean, the most obvious ones, of course, are stiffness and strength. For the material science students among us, we might know that stiffness and strength are 2 different properties. But for those of you who are here, maybe some of you might be guilty of using stiffness and strength interchangeably sometimes when you describe something. So when I say, so for example, if let's say I'm trying to break this pen, and I'm trying to break it, and it's very strong, I'll say it's very stiff. Am I right to say that? What is stiffness? Stiffness is how much a material can deform elastically. So when I say elastically, I mean that it's not supposed to fail plastically. It's not supposed to change shape permanently. So stiffness just means how much force is required to deform a material, but it can still go back to its own shape. What about strength? So strength is how much force you need to use in order to deform the material permanently or plastically. So the ultimate tensile strength of a material, basically it's for many materials, is basically the strength at which, the highest strength that you will experience as you deform a material, as you deform the part. But those two are two different things. If you don't expect your part to fail, then you shouldn't be too concerned about the strength. But if you are looking to design a part that is supposed to flex, if it's supposed to flex but supposed to go back to its original shape, then you think about what property are you looking at, and should you have a higher value or lower value? All these are very important for you to look at. So other than just these two properties, there are material properties that are measured statically or dynamically. So stiffness and strength, like that I just mentioned, they are so-called quasi-static or static material properties. So they are measured assuming the material is basically not moving in a steady frame. So let's say if I were to take my pen and I press it down, right now I'm pressing in front of the camera, it's not moving, right? The pen is not moving. So actually it's under static loading. The pen is experiencing stress, but there is no active, there's no movement, it's not moving, it's not accelerating. What about dynamic properties? The dynamic properties are, you'll be surprised that of course a material reacts differently. So some materials are very strong when they experience static loading. They take very high amounts of stress to break when you do it slowly. But when you do it quickly, sometimes it might not behave the way you want it to behave. So what kind of dynamic properties are there? Such things as impact properties. Okay. So when the material undergoes impact, most commonly there's something called impact energy. So how much energy is required to break apart something when you do it very fast? Let's say you throw something at it. It's different from when you load it slowly. And all these properties that I just mentioned, they can be found online in material data sheets. So I'll leave it up to all the teams to actually go through one by one of these three materials and look at what properties they have and what's the differences and how you might choose certain parts to be made from PLA, ABS, or PETG. And this is important for the challenge. You can choose to make different parts out of different materials. So you don't have to make every single part of your design out of the same material. So this is important, okay? Optimize your material choice. So before we press print, let's say, because you won't be doing the printing, I will be doing the printing for you. So before I press print, what do I have to do? Okay, so loading the file onto the machine is also an art in some sense. Okay, so to reach the printer, I have to input a G code. Okay, but before the G code, what do I have? So I have STL files. Okay, so STL files I can download online. Some of you might have already done so before. So I can download online from websites like Thingiverse, Sketchfab, or GrabCAD. And I would highly encourage all the teams here. Of course, you're not supposed to cheat. You're not supposed to download files online to submit. But it's not cheating if you're learning from other people. Okay, there are many good and interesting designs posted online. And I would highly encourage all the teams to go online and just do a quick search, look at what's out there and try to see how you can improve it. So from the STL, we can't print it because we need a G code, right? So we need to convert the STL to G code. So we need a slicing software. Okay. So, but other than just downloading the files of other people, what about your own creativity? You can turn your own creativity into STL files by using software such as SolidWorks or Fusion 360 or even Blender. So some of you might have experience with Blender, since Blender is free. Fusion 360 is also free. Of course, we already told you to download it. The education license is free and has most of the functionality. In fact, all the functionality, to my knowledge. SolidWorks, you require, you need to pay. Okay. So to slice your print, so it's important. I think we also told all of you to download Prusa Slicer or Cura. Okay. So Prusa Slicer is just the slicer that we'll be using for the challenge. Okay, but Cura is also compatible with almost every 3D printer out there. So at home, I use Cura. And why do we want you to download the slicer if you're not doing the printing? It's important because as part of the rules, we have a material limit for you to abide by. I think Vincent might have mentioned, it might have been in the details of the challenge. If not, we'll clarify later. So you are supposed to use a limited amount of material for your design. You can't just make something that is like, outrageously large or outrageously heavy. But how do you know how much material you're using? If you have your file, you slice your file. In every slicer, you'll be able to see an estimation of how much material you'll be using. In this case, you can see I'm using PLA, and my estimated length is 1.35 meters, and I'm using 4 grams of materials. Okay, so as part of your design considerations, you should think about how much material you need to use. If you're using too much material, where should you cut your material? Okay, but it's not just about how much material you are using. Okay, we want you to tell us how we want us to print your part. Okay, what is your print orientation? That's because different print orientations will require different amount of support material. Okay, you can see the baby Yoda on the left is standing upright. The baby Yoda on the right is lying 45 degrees. So which one do you think will require more support material? Okay, I don't really expect an answer from you. Okay, but of course, just looking at it right now, you might say 45-degree one will require more support material. However, it might not be the case. Take a look at the raised arm. I'm pretty sure I can use my hold on. Yeah, okay. Never mind. Okay, I'm pretty sure you can see my mouse. Yeah, so you can see that the baby Yoda has the left arm is upright, is raised out. So if your material is not touching anything at the bottom, it will require support because the printer cannot print in mid-air. It can to a certain extent, but you can see on this model color is yellow, but there are parts that are highlighted red. The red parts are the ones that are overhangs. Overhangs require support to be printed. If there are no supports, there will be a problem with the print. And the entire bottom side of the arm requires support. But you might not know it without slicing it. And the amount of support material is included in the total amount of material that you can use. So you have to think about just what orientation you need us to print it in. Otherwise, you might exceed your material use. And when you do your print orientation, what do you have to think about? You have to think about how to arrange your print to maximize print success. Like I said, the print can fail. If the red parts are not supported, it might fail. Okay. And at the same time, there are certain orientations that can allow you to decrease the amount of material that you need for supports. Okay. And how do you know it? Okay, actually, in your case, if you just work with Prusa Slicer and Cura, you have to do it manually. So it's by experience and by trial and error. There are software out there that can actually help you through some machine learning algorithm, optimize your print, like how to minimize the support material. Also, if it's possible, you can try to minimize print time. That's for my sake, okay? And also, 3D printed parts are not isotropic. This means that they don't behave the same way in all three different directions. I just talked about X, Y, Z axis. 3D printed parts don't behave in the same direction, in the same way, usually between the X, Y directions and the Z direction. This is something called anisotropy. But if you think about it, if I want my part to work in a certain way, how should I print it? If I print it in one way, it might be weaker than if I printed it in the other way. So something for you to think about. And other than the print orientation, we also want you to tell us what infill you want to use. So what is infill? Most 3D printed parts are not printed solid. Okay. If I printed this baby Yoda out, right, it wouldn't be one solid piece of plastic. Inside will be partially hollow. But what about the parts that aren't hollow? So in this example, this is a cubic infill. The infill density is 20%. So you can see the interior part of this cube. It is filled with some lines and filled with some open holes. If I use a 60% infill, you can see that right now the lines, the gaps are much smaller. This is a much denser and heavier cube. So this cube will be stronger, but it will also be heavier. It will also be different stiffness. So just what infill do you think you need to use? But not just the density. You want to know the pattern that you think is the best. For example, this is a gyroid infill. So you can see the shape is different. So even though it's the same as 20, it's 20% infill density. But you can see it's different. And if it looks different, does it behave in a different manner? The answer might surprise you or it might not surprise you. Okay, but it does. Different print infills have different mechanical properties. Some significant, some not so significant changes. But this is up to you to decide what infill you want. And of course, you can always feel free to Google or to ask your student ambassadors or even to ask me, on comments. I cannot tell you what to pick, but I can tell you what's the difference. Okay. But before we go into modeling, which is actually the meat of the lecture, let us think about what do we have to think about in terms of printing. So like I just said, support and infill, right? Other than those two, let's go into support again because it's very important. So supports, think about how much support do you need? And think about whether your support material can be removed. For example, if I have a rectangle shape and this is my part, all the blue lines are support material. You can see that I will not be able to reach into the triangle to remove your support. If I can't remove the support, then should we be placing it in the first place? And look at the side, there are simply too much support all along the sides. If I flipped this triangle upside down, you realize that I wouldn't even need any supports, right? So these are questions for you to think about and for you to learn. Other than that, we have tolerance. So what about tolerance? What is tolerance? Tolerance, for our sake, let's imagine we have a hole of a certain size. We want to fit something in. So how small should the gap between my inner and outer part be? And can I fit my part into the hole? For our case, for this challenge, okay, 0.3 mm is the smallest gap you can go, but 0.5 mm is fine. Okay, what this means is that if you have two parts that are supposed to fit together, if your inner diameter for the outer part is 5 mm, there should be a gap of at least 0.3 mm between the inner and outer parts. If your inner diameter is 5 mm and your part that you're going to put in is also 5 mm, it's not going to fit in. Okay, and if it doesn't fit in, your part, it's going to be difficult for us to even assemble your print. So this is very, very important. And for the challenge, okay, every single part of your model must be 3D printed. Okay, but this includes the locking mechanism. Okay, how are you going to put the egg into your 3D printed egg sleeve? If you put it in, can it remain closed? If you just have two parts and you put the egg in, you close it and I drop it. If the egg falls out immediately, then there's no point, right? You have to think about how you're going to keep the egg inside your part. And this design must be 3D printed. Okay, there are many ways of doing it. It can be a separate part, like a lock, or it can be just some kind of mechanism. Okay, but I won't give you any ideas here. You can search online, and I hope you can be as creative as possible. But I also hope that you can think about how easy it is to put in and remove the egg. Remember that for the challenge, we have to take out the egg in order to check if there are any cracks. If we can put the egg in, but we cannot take it out, then we are not able to check the egg for cracks. Okay? Or if it's very difficult to take out your egg, and halfway through we crack your egg as we take it out, we will give you another chance. Okay? We'll give you another chance, and it's up to that day itself. If we determine that it's by our clumsiness that the egg breaks, we will give you another chance. But if it's increasingly obvious that your design does not take into account how we can take out the egg without cracking it, then unfortunately, it's considered a failure. Okay? So this is also very important. So now, Fusion 360. Okay? I hope that after this challenge, some of you will go on to learn to use Fusion 360 even more, and maybe even learn to like it. Okay, because I did. Okay, sometimes just downloading models is just not fun. You need to do something by yourself. So I hope that you've already downloaded it. Some of you might already have experience with it. Okay, but if you log in for the first time, this is what you'll see. Okay, and what do I need you to do first? First of all, set your preferences. At the top right hand corner, you'll have your name. Okay, click your name, and you'll be able to find your preferences and go to unit and value display. Okay, and you'll see that there are things like general precision, angular precision, but what's important is, of course, we want you to use the correct units. So for our case, we are using metric standard. Okay. Also, there are default units. So because you can set your units to inches, but we are in Singapore, so we use SI units. Okay. And of course, Fusion 360 is not just a design software. There are many workspaces in it. Of course, the default is design, yes, but you can always choose to have different workspaces. And in different workspaces, there are different functionalities that I will touch on later. So the first step of drawing something is sketching. Okay, CAD software is based on making something 2D first, and then taking that 2D and translating it into 3D. But some of you might not be able to draw. So how? Personally, I couldn't draw to save my own life. I'll be honest. but thanks to computers, we have some very we have some tricks that we can play. Okay, so some simple steps to get us started. Okay, use a lot of references. And how do you use references? Okay, you can always import a canvas image. And of course, the first step is, of course, to create a sketch plane onto the canvas image, so you can sketch out what you want. Later, I'll demonstrate this. And to continue to learn how to sketch, we need to learn about the basic tools that we have, and the tools that let us draw less. 3D modeling is all about being lazy. Need to be as lazy as possible. So things like projecting shapes. If the shape is already there, can you just project it rather than draw it again? Yes, you can. Okay. But importantly, for 3D CAD modeling, we need to learn how to draw precisely. Okay. If a part is supposed to be 10 mm long, it must be exactly 10 mm long. If I have two lines that are supposed to touch at a right angle, they must touch, and it must be at right angles. Okay, so these are constraints. So I'll just demonstrate now. I will go into Fusion 360. I hope you can still see this. Okay. So let's say we have discussed how to design the egg sleeve that we want to, and we've drawn it out already. Let's say we discussed and someone in our team sketched out an egg sleeve. We can import that image into Fusion 360 to do our 3D sketching. So I'll just insert canvas. Okay. In this case, you can always insert from your computer. But for this sharing, I have created my default project, and I have included this image. So this is a TIE fighter. So I just select my plane. You can see that there are a few planes you can select. So decide where you want your sketch to face. Okay, so you import the canvas. So I've imported my canvas. So you can use the cube at the right-hand corner to navigate. Okay, if I click front, suddenly my view orientates to the front. You can zoom in with your mouse wheel. Okay, so you can see that this is a TIE fighter, and you can scale the TIE fighter up or down. Okay, you can also set it to be a specific scale. Okay, there are also things like the canvas opacity. You can make it slightly transparent. In this case, by default, it's 50%. I can make it 100%. Okay, 50%. And you can, so once you have this, you can start sketching. And how do you sketch? Okay, the basic of a sketch is deciding where you want to sketch. So first of all, create sketch. This is the first button beside your design workspace. Click it. You notice that it tells you can select these 3 planes currently. Okay. Let's say I want to select this plane. And now I'm in the sketching workspace. Okay. So what tools do I have? Okay, I can draw simple lines. I can also draw rectangles. Okay, I hope you can see my rectangle. I can also draw circles. Okay, and I want you to know that there are different types of shapes that you can draw. Okay, under the create, you can see that, okay, line is very simple. There's only one function. But even for drawing rectangles, there are different functions you can have. You know, you can have a 2-point rectangle. So you only have to select 2 points, a 3-point rectangle, or a center rectangle. For a circle, you can have a center circle, which is the default like I just did, or 2-point circle, or 3-point circle. So there are many, many ways for you to draw. Okay. And what did I say about drawing less? Okay. For example, I have my rectangle here. Do you see that this TIE fighter is symmetric? If it's symmetric, do I have to draw both sides? The answer is no. Okay. I would suggest for you to never draw both sides. Okay. If your part is symmetric, always only draw one side. Okay. That's because if you draw both sides, maybe you might not draw it perfectly and it won't be perfectly symmetric. Will it be important that it's not symmetric? Maybe, maybe not. Okay. So if I don't want to draw both sides, what can I do? There's a mirror function. Okay. I select my mirror function. I select my objects. The line here, 1, 2, 3, 4. Select my mirror line. But you realize, hey, there's nothing for you to select. So to draw a mirror line, just press L, which is the hotkey for line, and just draw a line down the middle. But let's say I only want to use this line to mirror my objects across, but I don't want it to be part of my actual design. What can I do? Select the line, press X. Okay, this makes it a construction line. Okay, so it's only used for references, but not part of the actual design. And now I can just click mirror. And then I select my mirror line in the middle. One, two, three. Okay, okay. Do you see that now I have my rectangle mirrored onto the other side? Okay. So these are basically simple drawing tools you can have, and not just mirroring. For example, if I wanted rectangles on the top and bottom, what can I do? You can just create circular pattern. Let's say I don't want my rectangle, I want this line. Select the line, click the center point, the one in the middle, and you see that now the default is 3 lines. So 1, 2, 3. Increase 1, 2, 3, 4. Okay. So it's up to you what you want to do. You can even control what angle you want to pattern it by. So all these are the basic sketching tools. But what did I say about drawing precisely? For example, you can see that there's a constraints tab here. So if I wanted my point to touch this line, you can see that when I mouse over, there's already a constraint here. This constraint tells me that this point is directly touching the line. If I remove the constraint, press the constraint and press delete. And now I can move this point all around. Let's say I zoom in, zoom in, zoom in, zoom in, and I put it very close, but not touching. And you realize I have a problem. You'll not be able to make anything solid out of this part. That's because, you see, this is not touching. But how do you make it touch? So if in case you made a mistake early on in your drawing and it's not precise enough, you can make it precise. I can click this line, can click coincident, and I can click this. And you can see that now automatically it touches the line. And now you can see that this becomes shaded because this is now enclosed. So these are just some basic constraints. Okay. So let's say once you are done sketching. So of course I don't expect to go through all the sketching tools with you, of course, in a few minutes. But this is just a quick warm up. So what can you do in the sketch workspace? But I want to make 3D CAD drawing, not 2D sketches. So how do we take something that's 2D and make it into 3D? So you can, of course, you can pull the part. If it's 2D, you can pull it to make it 3D. You can also spin it and revolve it, okay? Of course, it's just about finding the right buttons to click. It's as simple as that. So let me demonstrate. Let me go back to my sketch. Let me now draw a line. So how do I pull something? You can see that I can select this area. So I select it and I just press extrude. Okay. And then you can pull it and now it's a 3D part. Okay. What if I want to pull it on both sides? Very easy. Select the direction. Select two sides. Now you can pull it on both sides. Let's say, let's make it simple. Okay, one side. Let's say I don't want to keep it the same shape as I'm pulling it out. I want to make it smaller or make it bigger. Up to you. But how do you do it? Very easy. Go to taper angle. For example, if I give it a 1 degree, you can see that now it is slightly bigger. Maybe to make it more exaggerated, make it 5 degrees. Okay, anytime you click enter, you are done with the modification. But if you wanted to go and change it again, you can always go down to your design, your parametric timeline at the bottom of the screen and double click the feature. For example, you see extrude 1 at the bottom of my screen. I double click and I'll go back to the step where I was just now. And I can just go back and change this if I wanted to make it smaller, -5, and now it's tiny, -1. And create a new body. Okay. So this is pulling. What about spinning? So if I wanted to make a sphere, okay, of course, there are many ways to make a sphere. I can even make a sphere directly from here, okay? But let's say I don't want to do it. I want to do it the manual way. How do I do it? If I used, okay, now you realize that my sketch is gone. That's because I extruded something out. You can, but nothing is ever lost in Fusion 360. You can always find it. So you can either find it here in your browser or below in the parametric design timeline. Click the sketch and you can see that now if I click the eyeball button, my sketch comes back. Okay. So if I press E, E is the shortcut for extrude, which is the action that I did just now. If I press E now, I realize that I can't make a sphere. I can only make a tube. Okay, that's because you can't make a sphere by pulling something. But you actually can, just not pulling it outwards. So to make a sphere, I can use the revolve tool. So you can just select this face Then select the axis where you want to turn it around. And then you can see now you have revolved and created a sphere. Okay, I didn't select this part. Okay, but like I said, you can always go back and double click this. And now if I select this, okay, and you can see I have a perfect sphere. Okay, it's just about finding the right buttons to press. There are many functions here, such as extrude, revolve, sweep. Okay, I will demonstrate loft. So if I close this sketch and I make these bodies invisible, if I create a new sketch, let's say I create this sketch here, I make a rectangle. Sketch. Okay, you can sketch in more than just 3 planes. Okay, just now we can only see 3 planes, so these 3 planes, but you can create new planes. You can construct an offset plane. So I select this plane, can pull it up, and now I have a new plane. Click OK. And let's say on this sketch I want to create a circle. Finish sketch. Okay. Now I want to create this part. There is a square at the bottom and a circle at the top. How do I do it? Definitely I can't. If I pull this circle, I'll just get a cube. And the same thing for the square. But there is a loft tool, so I can click this profile and click this profile. And you can see now I have this part that I want. Okay, click OK. So there are many tools for you to experiment with. And you can create many, many different things just with very simple tools. Now, so let's say I've created my parts. We can do something called, body modification, because that's what 3D CAD is all about. It's not just about drawing something from 2D and just making it 3D. Okay, you can modify the 3D body that you just created. So we can do things such as booleans. So booleans are basically like logic. It's either plus, minus, or intersect. And of course, you can fillet it, okay? Not fillet, fillet. And you can shell the part. So let me just go through one by one what I'm talking about. So you can see that if I wanted, let's say I wanted to cut away some part from this weird shape that I just created. So I select my modify. You can see that there's this combine tool. So it performs Boolean operations. But it doesn't just combine. You can choose to either join, cut, or intersect. So my target is this body. My tool that I'm going to cut it with, let's change another one. Let's just use this. No, I can't. It's not. Let's just use the sphere. And now if I click join, you can see that this is now one part. But if I wanted to cut it, I didn't want to join it, I made a mistake. What do I do? Okay, like I said, you can always go back and change your option. So if I click cut, okay, and now I've cut this part. And now you can have this weird shape that maybe you could never have done otherwise. So what did I say about fillet? Sometimes you don't want sharp edges in your actual part because sharp edges are places of stress concentration. So they might cause extra stress on your egg or on your part. So what can we do to take away sharp edges? So there are two ways that industry can use to take away sharp edges. You can either fillet or chamfer. Now let me just demonstrate what the chamfer is, which is very simple. I click the edge that I don't want. So this edge is sharp and I don't want it. I can just chamfer it. Chamfering cuts away the sharp edge and makes it a flat plane. I hope you can see. I can make it more obvious. Okay, this is chamfering. Okay. Let's say I don't want to chamfer it. I can fillet it. So what's a fillet? Let's say I have this sharp edge here, which is also a stress concentration. I can attempt to fillet this edge. Do you see? This edge is no longer sharp, but it's now smooth. Okay. So this is called a fillet. It just takes a sharp edge and rounds it. So these are just two things you can do. And what did I say about shelling? Let's say I want to make a container or a cup, or maybe even an egg sleeve. What can I do? I can make it a shell. So you can remove the material from the part. So first of all, I would like to select my body, which is this body. And of course, I select the face. So select this face. And I can just shell it. And now you have a cup of sorts. Okay, so this part, it looks solid, but the interior has now been hollowed out. So these are all the different things that you can do for your part. Okay, 3D modification. And you know, just using all these simple tools, you can build something complicated from something simple. So I hope that you remember my canvas just now. So I imported this TIE fighter. So just by using the tools that I just shared with you, you can make something that is complicated. Okay, so this is something that I drew. So, you know, never overthink things. You know, you can always make something complicated by piecing together simple things one by one. Okay, so that is this is quite important. But other than just drawing, other than just drawing fixed shapes, you can also be creative, even artistic. And Fusion 360 does allow you to do it. So there's something called free form modeling. You can think about it like you're shaping a clay pot, like a clay pot. Okay. And how do we start? Okay, to start, you just need to click this purple cube here, and we'll be able to go into the freeform workspace, and then you just need to use these two buttons. So let me demonstrate. Let me hide my canvas, hide this body. Do you see this purple cube can create a form? Let me just select a box, and I select this face. Let me just draw a box here. So now I can create this box. Okay, click OK. And now with this box, what I can do, I can modify this box. I can click this point, way down, click this, can move it this side. No, it's basically like plasticine. You can shape it however you want, and not just points. You can click faces. I can pull it out. I can even scale or rotate the face. Okay, so there are things that you can do. and to create new shapes. This might not be very precise shapes, but not all shapes need to be precise. But you need to know what you want it for. And if you find trouble in drawing 3D shapes, you can start off by modeling something in freeform first to provide yourself a reference. So now that you are done, let me finish my form. You need to export your model because the Fusion file is not STL and I can't print your Fusion file. So I need to save as mesh. Under the bodies tab, under the bodies, in the browser, if you right click it, you can see this option, save as mesh. Click that, and you can see that now this window pops up. I would like you to select either STL binary or STL ASCII. Okay, either is fine. 3MF is a new file type, but let's just stick with what we know as a demonstration. Click body form, right click, save as mesh. Okay, and STL binary. And then I can just save it to my computer. And that'll be all. Refinement, medium usually works. Unless you have a many small fine features, then maybe you need to go high. But from my experience, medium is fine. So, and that's basically it for modeling. But like what Vincent shared, nowadays we have so many tools at our disposal. Is beyond just modeling, we have the ability to think about how our model performs and how we can do it. So you can do FEA in Fusion 360. It's really like a calculator, okay? Just a slightly more complicated calculator. So there is a native simulation capability in Fusion. First of all, you have to save your file. And after saving your file, just go to the workspace, choose the choosing area, and just select simulation. And what study should we pick? Okay, static stress, which is the first one that comes up, is the most simple one. Like I said just now, okay, if I take this pen and I were to press it, compress it along the z-axis, I'm exposing it to static stress. And you can run this kind of simulations to see whether your material will fail or not. But for our case, we are doing something like an egg drop. So egg drops are not static, they are dynamic. It's like an impact. Okay, so we want to do an impact test. So for this challenge, the more suitable one would be event simulation. But however, I would like to tell you that you cannot solve the impact test locally. You can do cloud solve for free, but you cannot solve it on your computer. Later, I will show you what I mean. So the basic simulation workflow in Fusion is very simple. It's basically A, B, C, D, E, okay, 5 steps. First of all, once you go into your simulation workspace, you'll see these buttons. Just follow it in sequence. First of all, simplify. Is your model very complex? Are there unnecessary details? If there are, you can remove it. What is your model made of? So you can decide what material your model should be. Is it plastic? In this case, yes. What kind of plastic? Okay. Or maybe in the industry, maybe they use steel, titanium, aluminum, or whatever, right? What constraints? So when I do my simulation, which parts are fixed? So which parts are not supposed to move? And of course, if I, impose my load, so which parts are supposed to move? And if I'm doing an impact test, definitely I must have 2 parts, right? So one to hit the other. So which parts will touch or are touching at the start of the simulation. So these are just the 5 key considerations. And after you set everything up, you need to prepare to set up the solution. Okay, click Manage, which is this box here, and you'll see that there are 4 things for you to look at. There is General, Mesh, Damping, and Output. In this case, we can ignore damping. Okay, let's look at General. The most important thing you need to look at is how long you will simulate, total event duration, and the number of result intervals. The more intervals you have, the more clearly you can see what's happening in the event. If your model, let's say, if I'm starting out too far, let's say I put my egg 1 cm away from the ground, in 0.001 seconds, it will not even touch the ground. So the event duration needs to be properly set up. How long should it be? But it shouldn't be too long. The longer it is, the longer it takes to solve. Then there is the mesh. What size mesh should I have? Okay, if I have an egg, yes, and my egg, if I only used 1 element to represent the egg, how accurate is this? But if I use 1,000 elements to represent my egg, is it too fine? Do I need that resolution? It's up to you to decide. And finally, the result output. So what are you trying to find? The stress, the displacement, the strain, all these things, you need to decide what you want to know. And once you've done everything, you want to view your results. When you finish solving for the first time, you will automatically go into your results window. But let's say you are going into you're going to someone else's file, you're trying to look at the results. So you can always click the results button and you will show up. And you go into the results workspace. So the most interesting one maybe is the first one, the animate button. So you can always animate your results. So in this case, I've animated an example. If I play it, you can see that it is bullet-shaped object made of titanium that is impacting aluminum sheet that has been deformed by it. Okay. But it's not just a cartoon that we are trying to make. Okay, we want to see the stress, the maximum force, the maximum deformation, all these things, and we can see all this by inspecting our model. So all these tools will help you more take a better look at what's actually happening in your model. So let me just go to the Fusion 360. So you can see this is my model simulation. I would like to tell you also, this is very important. If you simulate an event, you can give it an initial velocity. Okay, initial linear velocity. So which is what I gave this object. But you realize that it's not touching. Okay, but it's very, very close. The closer your object is to the surface is going to impact, the faster the impact will start. Okay, if your object is too far away, it will take too long to compute. So you have to start very close to the surface. This is important. Okay, for this case, I don't have to simplify my model. It's already very simple. For my materials, I can click materials. And you can see that I have already set the materials here. My plate is made of low strength aluminum. And my projectile is titanium. Okay. Okay. My constraints, you can see a lock button here. So I have constrained the 4 sides 1, 2, 3, 4 sides of this plate to be fixed, so they are not supposed to move. And I'm given a load to my projectile, an initial linear velocity. I can select the angle. You can see that there's an angle I can select. Okay. And by selecting the angle, you will change your simulation. So think about how your part is going to hit the floor. Is it going to hit it in a certain way, or might it fall in a different way? It is up to you to think about. Okay. Context. Okay. You need to make sure that you generate your context. So you can global context. You can just generate context. If your model is fine, it should normally auto-generate. You can always check it. So I click here, context. I can see that between my two bodies, there is a separation context. So between body 1 and body 2. And then after I'm done, I can just go to manage and set my settings. Click OK. Click solve. Okay. Take note that you cannot solve this locally. But for education account for Fusion 360, solving on the cloud is free. So it doesn't even use your computer resources. It just sends it to the Autodesk server. But you cannot control how long it might take. Okay. So you can, and for, credits are free for students. So just click solve. And then it will tell you how is it going. Then once you're done, click results. That's because I changed it. Okay, so because I've changed the settings for the velocity. That's why now I have to recompute the results. But the results will be the same as what I'm showing here. Okay, and you can just use all these tools to take a look at the results. And that's basically it. Okay, so with that, I've come to the end of my part, the lecture. And I'd like to just tell everyone that, this is not really a competition. Okay, we want this to be a conversation. So if there's anything that you want to try, be bold, but you are not sure how to do it, feel free to ask us. Okay, we're not helping you with your model, but we can help you to learn. And when you learn, you can make a better model. And also, maybe we can also learn along as well. So you can always get in touch with your student advisors, or you can contact me. Okay, I'm in the Telegram group chat. So, or you can email me. So I will try to get back to you as soon as I can. So now it's Q&A. So is there any questions that you guys have regarding the competition? So are there any questions? So I have a question from someone. Yes, you can. So there are 3 materials for the challenge. There's PLA, ABS, and PET. You can design with different materials for different parts of your print. Okay. And also, I would like to emphasize that for the challenge, it's a free drop. Okay. So your model, your 3D, your X sleeve. Imagine if you printed a rotor, right? We won't spin it before we drop it. Okay. We will just hook it, then we'll drop it. You can think about how you want us to drop your model. So you should include a small ring for us to tie a hook around to attach your model. So, and based on where you put this ring, your model will drop at a certain angle. For those of you who don't put any ring for us to attach our hook to, we will add the ring ourselves to your model. Is there any questions? No questions? Anything?
Guys can unmute yourself if you want. Otherwise, you can always look for us, Yong Hao in particular, or your student ambassadors to, help you with any queries.
Okay, thanks, Shi Jian, for the thumbs up. At least you are there. Okay, if you have any questions, or any very creative ways you think you have of trying to tackle this drop challenge, please reach out to your student ambassadors, okay, or reach out to us, and just share with us what you plan. If you're afraid that it might break any rules, tell us early, and we can talk about it and see whether it does break any rule or not.
All right. So let's just wait for a couple more minutes. Right. So so I think I echo what Yong Hao has mentioned. So if you have any question regarding what is allowed, what is not allowed, please sound off right now. If not, we assume that everybody knows or have jotted down what Yong Hao has mentioned during the talk, right? But I also echo what Edie has mentioned. If you have any questions, you are being attached to student ambassadors. So feel free, talk to them. If you want to reach out to us, go ahead. We are in the Telegram group. Okay, so for those who are in the Telegram group, we are there. So just sound off to us. So I think more importantly is actually to get Yong Hao's information. Can you flash your information just once more? That is very important, because if you have any question, that's where you should really try to get help from. Okay.
Yeah, I mean, really, I need to emphasize, if you have anything that you want to do, but you're not sure how to do it at the moment, of course, I encourage you to learn it by yourself, but you can always approach us and ask us about it, and we can learn together.
All right. So I think, not sure whether Yong Hao has mentioned this, but this is very important that you create your own ink sleeve. I guess there are always design available online, right? So, but I think the point here is really to have fun. I think what Yong Hao has said is more of a conversation, not only amongst your friends, but it's a conversation with us, right? So we learn more when we talk to more people. So try to talk to us and also the student helper, student ambassadors. Right, if there's no question, may I move on to the next one? Next part, right? So let's just move on to the next part. Let me find, I switch it off. That's so strange.
Still got people coming in the room.
All right, so I'm proud to maybe showcase our student ambassadors once I find this one. Okay, so all of you, all the teams here will be assigned to a student ambassador. So one student ambassador will be helping you during the design stage. So feel free, communicate, converse with our student ambassadors. Right, let me just introduce you one by one. So we have Victoria. She's our student ambassadors to Excellent. Right. I mean, I like the team name. Excellent, right? So yeah, so Victoria is our year one students. I know she's very fresh, just joined us, but I think here is that she's very interested in the different properties of material. I think that can really make a big difference, right? When it comes to designing which materials that you should use for the challenge, right? Then let me introduce Tran. So Tran is the student ambassadors to IC per experimentist, right? So experimentist, okay, that's also quite a good pun. So here she's our second year student, and of course she has more knowledge in material science, and I think here she's quite active. Okay, not only in material science, she has a minor in business. So if you're interested in business, minoring in business, feel free to talk to her. Okay, then I think here is because what we are interested in is to really see what they have wrote about why they joined material science. So we'll make this available, all the biography to all of you once this is over. So we just maybe put it distribute this file. Right. Then for Joel, he's our student ambassadors to as X section. All right. So I think he's doing really well in our material science, and I think he's our second year student as well. So please feel free. I think he's also very interested in the nanomaterials, biomaterials, and how this the properties can be used in the real world situation. So that actually is very applicable to what we are doing right now, right? So Corinne, she's our student ambassadors to Tamago Splat, right? So she's our third year students, and definitely she has way more experience here, and she's also very active in our student event. So feel free, if you like, you can always talk to her about what you want to know regarding material science or NUS or in general, engineering. All right. Then we have Jody. She's our student ambassadors to CS4. So she's our final year students, but technically she's, I think, year 3 student right now, but she's a engineering scholar. So that takes her 3 years to finish her bachelor here lah. So I think it's quite interesting because she also has some experience in the internship. So feel free, if you're interested in some internship program, understanding how it's like the internship in applied materials, and feel free, talk to her. So Win Johnson, so in short, just Win. Win is our student ambassadors to 8 Guardians. So Win is slightly different. Okay, so he's our PhD candidate. Okay, so Win has received his diploma from Singapore Poly. So if those people from Singapore Poly, I think please just talk to him about how's his education career over that few years. Right, so currently he's also doing 3D printing, and I think here he's very interested in the structural and functional ceramics material. So we have that. Okay, that is our student ambassadors to group 8. So I think it's J2, if I'm not mistaken, the new team name. So that is our 4th year student. So he's very curious about what nano material is all about. But at the same time, I think for this course, I mean this challenge, please feel free to also look at it at a microscopic level, okay, if you want to. Then we have Hong Chen. Hong Chen is our student ambassadors to Hing Hing. Okay, so Hong Chen is currently the 4th year PhD student, and his research topic is basically the if I'm not mistaken, is the polymeric materials. So I mean that's a good area because you are going to use polymers for this challenge. So make good use of his knowledge. So I think with that, basically, I think I will conclude the event. So the very first part, the first phase of the event is simply to equip you, all of you, some basic knowledge in 3D printing, and also how to use computer assisted design software to come up with something that is useful, right? So that is your prototype. So you can use this prototyping skill not only pertaining to this challenge, you can use it for anything else when you go into your university life, or even if you step into the workforce, right? So the next thing that we want you to really know about is the finite element analysis. So finite element analysis is also a very powerful tool, not only to study the impact of a material. You can also study the temperature distribution, right, or within that material. So that could be a very important case. I mean, when it comes to, let's say, thermal management in Singapore. So with that, I would like to really close this session. But before I do that, right, I will ask all of you to meet your student ambassadors. So during the meetup with your student ambassadors, please do not be shy, switch on your camera. So everyone try to switch on camera. So our student ambassadors will also switch on their cameras so that you feel that you are like, it's quite hard because everyone is like, there's no videos and I feel like I'm just talking to the computer, right? So it'll be great if you can put on your cameras on. Okay, everyone do that. Then later on, I will open the breakout room. So I have already created all 8 breakout rooms together. I mean, I've allocated all of you there. So if you feel that I have assigned you wrongly, please let me know. Okay, come out to the main room, let me know. So during the session, please do some discussion, talk, introduce yourself, and then basically you will end off from the breakout room. All right, any questions so far? So this is the last chance for you to ask question to Yong Hao or myself or Edie, okay? So please make use of that. I'll give you maybe like, we will start at 5:15. That's basically 3 more minutes to 5:15. So ask the question before you meet up your student ambassadors in the breakout room. Okay, so I'll let the student ambassadors handle the breakout rooms from there on. So the student ambassadors will dismiss the teams. So any questions before we open the breakout rooms? No, if you're shy, just write it in the chat.
Okay, Yiheng from MP has asked, how much material can we use?
Okay, so the material that we can use, I will basically translate this information to the student ambassadors, but currently, as far as I understand, I think back then we were saying it's about 200 grams.
250, I think
250 grams? Okay.
Yeah, so 250 grams including your support material.
Yeah, 250
Actually, it's quite
grams.
a lot. It's quite a lot. So 250, okay, including support material is a total. So like I said, you can use different materials for different parts, but when you add it up all together, right, cannot exceed 250 grams.
So not to worry, we will disseminate this information to the student ambassadors, so they will have a copy of the so-called the constraint, okay, to the design constraints. So we will share these constraints via the student ambassadors, and also at the same time, if you are in the Telegram group, we also share it there. We will also share it there. Any questions? If not, I need to find. Let me just stop share. Okay, we have 1 last minute. Okay, so if there's no question, I'll put you all into your breakout rooms. Okay, so let me just try to get it done. So because this is the first time I'm doing it, so bear with me if something goes wrong, right? Hey, thanks. I
so fast you
think
assign already.
yeah, all
I was
assigned
still
already.
looking. Okay.
Yeah, because
Short.
I do things, I don't like to do it too slowly. So let me.
Can either
Sean,
stop
why
or
is
pause
Sean?
recording already. You can stop recording already.
I
actually.
can stop recording already. So